values x can take, it is possible that none of ai occurs, then in that case it's going to take value 0. It is possible that one of the ai occurs actually, so one of the a1, a2, an occurs, so then in that case it's going to take value 1 because the rest are going to be 0. Or 2 can occur, or even all can occur actually. So if all can occur, each one of the xi will take value 1 and their sum is going to give you the value n actually. Now let me denote, let me get a variable, for example, let me define a variable y. Okay, next, define a variable y. So this variable is that, okay, y is 1 if x is bigger than or equal to 1 and equal to 0 otherwise. So what does this y, how you can interpret this y actually? Y may be interpreted as that it's a random variable that is saying that at least, so if x is bigger than or equal to 1, x would be bigger than or equal to 1 if at least one of the a1, a2, an occurs actually. At least one of the a1, a2, an occurs. Okay. By the way, what are the interpretation of the probability of a union of ai? This probability may also be interpreted as that what is the probability that at least one of the a1, a2, an occurs. Okay, this is what an interesting kind of the observation is. Now what can be the relationship between x and y? I mean, if you think about it, x can be 1, okay, if x is 1, okay, if x is 1, then y is going to take value 1. But x can also take value 2. In other words, at least, 2 of the events may also occur. What would be the value of y when x is 2? Y is still going to be 1 actually. So you can immediately see that x is always bigger than or equal to y. X is always bigger than or equal to y. And if the x is bigger than or equal to y, this implies that the expectation of x is bigger than or equal to expectation of y actually. Okay? Expectation of y. Now let's calculate the expectation of x. Expectation of x is equal to the expectation of sum of I equal to 1 to n xi, which is same as sum of I equal to 1 to n expectation of xi. And what is the expectation of xi? Okay, you know about the indicator function. Okay, the indicator function ia equal to 1 if a occurs and equal to 0 if a does not. Otherwise case. Okay, otherwise case. The question is, the answer is that ia takes two values, 1 and 0. So the question is, what should be the expectation of the indicator function of a? We have calculated it previously that indicator function of a takes two values, 1 multiplied by probability that a occurs plus 0 multiplied by probability that a does not occur. And hence the expectation of the indicator function of a is equal to the probability of a. So this is a key and a major identity that you always have to keep in head, that if you have an indicator function and its expectation, it's equal to the probability of A. Now, using this, my xi is really the, what do you call, sum I equal to 1 to n. I can say that this is same as the, because xi is the indicator function of ai, okay, and what is the expectation of indicator function of ai, so it is going to be equal to, what do you call, I equal to 1 to n probability of ai. Okay? So the expectation of x, explicitly we can calculate it to be this number. Now, think about the expectation of y. Okay, what would be the expectation of y? The expectation of y means that at least one of the a1, a2, an occurs actually. Okay, you can also call it that this expectation is equal to the probability. So y is actually the indicator function. I mean, if you see, y can also be treated as the indicator function of a1 union a2 union an. Okay, and y, it can be the case that y is going to be equal to 1 if at least one of these occurs actually, and y is going to be 0 if none of a1, a2, an occurs. So this has the same description as this. Okay, x is the number of events that ai occurs. That if I say that at least one occurs, this means that x bigger than or equal to 1. So in other words, I can treat the expectation of y as the expectation of the indicator function of a1 union a2 union an. And if this is the case, the expectation of the indicator function is basically the probability of this actually, probability of a1 union a2 union, what do you follow, an actually. So I know that expectation of x is the sum of the probabilities, expectation of y is the probability of union. So if you substitute these two values here, you have your Boole's inequality. So you have a very interesting way to prove the Boole's inequality actually. Okay. Let's do some more fun with this identity. The key thing that is helping you here is this property that the expectation of the sum is the sum of expectations actually. Okay. So there are some examples that I'm going to do, and I'm going to leave the rest for you to do for you actually. Okay. So you also have to work a little bit harder to work out these properties or apply these properties actually. So for example, now I say that, okay, that I have an x that is binomially, so this is example 2e from chapter 7, binomially distributed with parameters n and p. Okay. Now x may be interpreted as that, okay, you play for example the coin toss game for n times, or you are taking n exams, and in each exam you have a probability p of passing it. Okay, you have the probability p of passing it actually. Now if I say that xi means xi is going to take say value 1, where I is 1, 2, 3 up to n, so it can be anything up to n. Okay, xi means xi is going to be 1 if ai occurs. Okay, ai occurs, and let's assume that ai means you passed you passed ith exam. Okay, so if I'm saying that you are taking an exam and in each exam you have a probability P of getting success, then xi means that you pass the ith exam, and it's going to be 0 if you fail. Okay, otherwise. So xi can be treated as the indicator function of ai. Okay, xi can be treated as the indicator function of what do you call ai, where the ai means that you pass the ith exam. Now, then x can be treated as the number of exams that you passed. It could be 0, that you didn't pass any exam. It could be that you passed one exam. It could be that you passed n exams actually. In fact, you can write this x as the sum of outcome of the first exam, where x1 is what? The outcome of the first exam. In other words, x1 is going to be 1 if you pass the first exam, x2 and x1 is going to be 0 if you fail. So you can also write this x as x1 plus x2 plus what do you call xn. By doing this discussion, what actually I am saying, that every binomial random variable is basically the sum of n Bernoulli random variables actually. So here, with this interpretation, if I say that x2 means that you passed or failed the second exam, and xn means you passed or failed the second exam, depends on it. So the x is really the sum of it. If x is, we interpret x as the number of exams that you passed or failed actually. Now, if I want to compute what is the average that you're gonna get, what are the number of exams that you're gonna pass on average actually, okay? By the way, if x is binomially distributed, we already know its average actually, so it's NP. The question is, are we going to get NP through as well this actually? So this is going to be the expectation of x1 plus up to what do you call xn, and hence I can also write this as that this is equal to the expectation of x1 plus, or maybe the sum that goes from I equal to 1 to n expectation of xi, where the xi is the indicator function. And this indicator function takes two values, 1 and 0. So I can say that this is going to be a sum that goes from 1 to 0, 1 multiplied by the probability of passing the ith exam plus 0 multiplied by probability that you fail the exam actually, ith exam. And if you simplify, it's going to be I equal to 1 to n probability of ai. Okay? But we know that what is the probability of a passing the ith exam? This is equal to precisely p. So this is same as having I equal to 1 to n and p. So in other words, you are adding the p n times. So this is equal to precisely, what do you call, np. So what do you saw actually? That we computed the expectation of binomially distributed random variable by breaking that binomially distributed random variable into n Bernoulli trials and using the identity that the expectation of sum is the sum of expectations. So that's a pretty interesting and important thing that we should keep in our heads. I'm not going into the all examples. I leave as an exercise for you to read the example 2f. Okay, I did 2e, 2f, 2g. So the 2f is about finding the sum of n negative binomial random variables, and the 2g is about the sum of n hypergeometric random variables actually. So if you know the expectation of each one of these, in other words, you assume that x1, x2 and xn are hypergeometric, then we know their expectations. The question is that what would be the sum of those expectations actually. So you have to work out for themselves actually. Let me do a last example, and then maybe we can move to and maybe you should do the example 2J as well. Okay. These are very interesting examples, okay? Interactive, very interesting examples. So let me do, say for example 2H. 2H example. So the 2H example is related with the matching problem. Example 2H is about the matching problem. If you remember, we have done this matching problem in several ways. So we say that you have a room with the n people in which every person has a hat, and what they do, they throw their hats, say for example at a certain location in the room, say in the middle of the room. Then those hats are mixed up, and then everyone of each of the n goes and picks up his hat actually. Okay? What are the probability? So we considered and studied basically the probability that at least one of them is going to get its own hat actually. Its own hat. Okay? So this is what that we studied. But now what we would like to do, we want in this situation, I want to find the number of people in this situation, number of people, expected number of people on average, expected number of people who get their own hat, who get their own hat. Okay? Let's give this random variable a name. So let's call x as the number of people who get their own hat. Okay? So let's give this random variable a name. What do you call x? Okay? Then x is this number, and let's denote that xi means that the ith person got his own hat actually. So if I say that ai is the event actually, so let me say that xi means that the ith person, the hat that ith person gets. Now there are two possibilities. Either the ith person is going to get its own hat, or it's going to get someone else's hat actually. So I'm going to say xi, I'm going to assign it a value 1 if person gets own hat, and it's going to be 0 otherwise if he doesn't. Okay? And if x represents the number of people who have got their own hat, then this x can be written as x1 plus x2 plus up to say xn, because there are n people and n hats. So what is the interpretation of x1? You know x1 would be 1 if the person number 1 got its own hat, x2, and it would be 0 if he doesn't, and similarly x2, xn. So x is going to be the total number of people who got their own hat. So what is our question? Our question is to find this expectation. Find this expectation actually. Okay? So this expectation is going to be equal to the sum of expectations that goes from 1 to n, expectation of say xi But this is really, this expectation or xi takes two values actually, okay? So it takes two values. So it's going to be the sum of 1 multiplied by the probability of getting own hat. Let's call, say, this event AI. So it's going to be 1 multiplied by the probability of AI. AI means that person got its own hat, plus 0 multiplied by the person that didn't got its own hat actually. Okay? This is what that you're going to get. This is going to be the value of the expectation by definition, because xi takes only two values. So what would be the final outcome? The final outcome is going to be that the expectation of x is going to be the sum of I equal to 1 to n probability of AI. Okay? Probability of AI. Now what is the probability that a person gets its own hat actually? Okay? And we have computed it several times in several instances. This is equal to 1 divided by the total number of people actually. So in other words, this is going to be equal to 1 divided by what do you call n. And there is a reason behind it actually, because so it's like, okay, you have n hats, and what is the probability of choosing one particular hat actually, which is my own hat out of these n hats. Now all n hats have an equally likely probability of being chosen. Okay, so the probability of choosing the own hat should also be what you call 1 over n. Okay, so it should be 1 over n actually. So it's like you are summing 1 over n for n times, so it's going to be n times 1 over n, so it should be equal to 1 expected. So in other words, if you have n people, that's a very interesting result actually. If you have n people who are throwing their hat in the middle of the room and then taking back the hats, that on average there will be one person who gets what do you call his own hat.